about time. So I'd like to introduce today's speaker, Dr. Mohan Sarovar, who is a longtime collaborator and a dear friend to me. Mohan did his Bachelor of Science and the Master of Science in Electrical Engineering at Cornell University. And he did his PhD in quantum information theory and quantum control at University of Queensland, Australia, under the famous Milburn and Nielsen. Then he moved to UC Berkeley, working with Whaley for quantum information science research. Then he moved to Sandia National Laboratories in California and worked with me and others for various quantum optics and quantum information science, including quantum communication, quantum computations, quantum simulations, and quantum sensing. Mohan is currently a co-director of the Quantum Algorithms and Applications Collaboratory Group, in abbreviation QuAAC, in Sandia. So Mohan is one of the few who worked on almost every aspect of quantum information science with a depth. He is now a distinguished member of technical staff at Sandia National Laboratories, and that distinguished member of technical staff is only top few percent. His work has been covered by many media on many occasions, and he also gave numerous invited talks about quantum information science research. Mohan is actually an intellectual leader in the broad field of quantum information science and research now. Let's welcome Mohan.
Thank you, Daniel, for that somewhat embarrassing introduction. And thank you for Colloquium organizers for this chance to present some of the work that we've been doing at Sandia here. So as I said in the abstract for the talk, I'm going to try to give you a good picture of the range of work that we do at Sandia, specifically in the fields of quantum algorithms and applications. Most of that is consolidated under this group that we have, QuAAC. That's a duck as a quantum circuit, if you can't make that out. And so what is QuAAC? So we're a group of about 40 staff, postdocs, and students studying applications of quantum computing and quantum technologies more broadly. We're geographically very distributed, New Mexico and California. Obviously, this is where the Sandia sites are. But then we also have a bunch of remote workers all over the US, Texas, and including Arizona. And the broad questions that motivate our work are basically these two. What might quantum computers be used for, and what kind of advantages might they offer over conventional classical computers? And so they're fairly broad questions. And if you look at quantum computers in the news, you might think that these are kind of questions that have already been worked out, right? So people are apparently using quantum computers to predict floods, to execute tasks that would normally take 47 years instantly, and a lot of other things, right? So as you probably all know, these are kind of exaggerations. And in fact, quantum computing is much more nascent than all of that. And if you want to think about where the field is as a whole, I think a useful way to think about it is in this two axes. The number of qubits you have available in a quantum computer and the limiting error rate that you might have. Right? And where we are right now is roughly where this red star is. Maybe hundreds of qubits or 100 qubits, and limiting error rates, depending on the platform, of 10 to the minus 1 to 10 to the minus 2. That's the probability of an error when you do a gate on a quantum computer. And these shaded regions are roughly what you can do in each of these, in the regions on this graph, right? So if you have too few qubits or your error rates are too large, then you're basically in the classically simulatable regime. You're not doing anything that a classical computer can't already do. Right? If you're way over here, where you have many qubits and your error rates are really pretty low, you can basically use your textbook description of a quantum computer. You have a fault-tolerant device that can do many useful quantum algorithms, right? At least some useful quantum algorithms. And then there's this huge chasm in the middle where you don't have enough qubits and your error rates may be on as low as you'd like, where we don't really know what the uses of these computers might be. There are some posited uses for near-term devices. These are called near-term devices. but I would say they're not nearly as established as these fault-tolerant applications that we know about. Okay, and so this is where we are, and although we would like to get to those applications where we're predicting floods with quantum computers, for example, there's a long way to go, and that's really what QuAAC is focused on, right? So if you go back to those questions, what might quantum computers be used for, and what kind of advantages might they offer over classical computers? It turns out to answer those fairly simple questions, you need to take a very broad view of quantum computing. Quantum computing has many levels of detail, right? All the way from what devices you're using to what actual applications you're targeting. And you need to take an integrated view of all of this. And that's what we try to do at QuAAC. And so, why would you care about device models and architectures? Because that goes to looking at the question about what is the best way to build quantum computing hardware to deliver quantum advantage. Right? Of course, you might care about algorithms because that's eventually what you're going to be implementing. So we try to design new algorithms and do analysis of algorithms in a very rigorous way. The step above that, resource estimation and performance assessment, we work a lot on realistic estimates of hardware resources that you might need, especially for fault-tolerant scale algorithms. These are algorithms that you typically, these are the kind of high-profile algorithms like factoring or simulating materials that you see. And although we have complexity arguments to say that they will be asymptotically more efficient than classical computers, there's a lot of work that needs to be done to really understand what the constant factors are in these complexity arguments, right? So there might be exponentially better, but if your constant in that exponential is very large, you might still want to do it with a classical computer for certain scale problems. So we try to put real estimates in terms of how much hardware you need, like what number of qubits, what error rates. And then we also spend a lot of time evaluating hardware to see if it's suitable for execution of certain algorithms. And then the next kind of level up the stack, there's applications. So these I distinguish from algorithms in the sense that these are kind of applications of quantum technologies that might not just be straightforward computing, right? You might be using a quantum computer as a component in a larger application. And I'll talk about one example in a second to make that a little clearer. And then finally, advantages. Of course, this is, we want to point to rigorous advantages that you might have with a quantum technology, right? And we spend a lot of time trying to rigorously quantify what that advantage is with any algorithm or technology. Okay, so that's kind of an outline of what we look at, and the picture I want to kind of emphasize is that integrated approach, right? So we try to work on all of those aspects at once, and I want to give you a couple of highlights or a couple of kind of vignettes of research that we've produced recently. One is a new algorithm for simulating light-matter interactions. Another is a concept of a quantum computer-enabled optical receiver for classical communication. I tried to pick these because I thought they would be more interesting for this audience, being the College of Optical Sciences. And then for the bulk of the talk, I'll kind of do a deep dive of one recent result, which is focused on verification of quantum computers, right? So if you have a large-scale quantum computing, quantum computation, how do you know whether it's correct or not when it spits out answers? Okay, and then I'll conclude with a kind of brief look into the future. So let me dive into the short vignettes now. So this is a paper we put out, I guess, earlier this year, a quantum simulation of weak field light matter interactions. It's a collaboration with Hamad Hafna from UC Berkeley. And what we were interested in is, so Hamad's lab works on ion trap quantum computing, so trapped ions. What we're interested in is, can we use trapped ion platforms to simulate weak field light matter interactions? So what do I mean by weak field light matter interactions? It's basically where you have a matter system that's interacting with fields that contain few photons, right? So very weak intensities. And that's important for understanding things like the efficiency of photosynthetic light harvesting. So if you look at biomolecules, pigment protein complexes, they typically see very few photons. And so understanding how they absorb those photons and how they work, that's one reason to look at these kinds of interactions. Modeling photodetectors with nanoscale structure. So if you have nanoscale structure in your material and you're trying to build a photodetector that's sensitive to one or few photons, you want to really understand what these interactions look like and how absorption at that scale looks like. Okay, And the important thing here is that when you have a few photon wave packet, you cannot treat that semi-classically, right? So you can't treat that as an electric field with some amplitude. You have to quantize it and deal with it as a quantum field, right? A multimode quantum field. And so what we started was to think about quantum computing architectures like trapped ions, cavity QED, circuit QED, and notice that they have bosonic modes lying around, right? So typically when you have a cavity structure, you have bosonic modes lying around that you can control. And they also have localized entities, like in this case, calcium atoms in trapped ion. In the trapped ion case, you have atoms, and the bosonic modes are vibrational modes of an ion crystal. And so can we use this bosonic mode to basically mimic a optical field or an optical mode? It's not that simple, because on the left here with a wave packet, you have a propagating optical mode, right? Optical field, and here you have a stationary cavity mode. And so at the outset, this might not seem like a nice mapping between the two, but you can actually make use of those those bosonic modes. And what you have to do, however, is do a dynamical simulation that mimics the interaction of the localized system with the propagating field, right? So what you end up doing is you reconstruct Green's functions or response functions of the material system to this field. So you can think about this as, you have time going along some axis, and any particular Feynman diagram for this weak light matter interaction consists of the matter system interacting with the mode instantaneously, right? So or with in a delta function like interaction. That's what the Green's function encodes. And if you can mimic that in your quantum computer, you can effectively reconstruct the Green's functions for the system's response. And once you have the Green's function, you can reconstruct any material property that you might want as that results from the response of the field. It's not so important what this expression is, but this is just to show you that this is a convolution between some field properties. These are the field profiles, temporal profiles, and the Green's functions that you've reconstructed from your quantum simulation. So this is just an example here. I have a wave packet. It's a Gaussian wave packet here containing a single photon in this case. And the black dashed curve is the exact response of an atom when it sees this propagating Gaussian wave packet, right? And the blue curves are what you reconstruct with this quantum simulation approach, where you first reconstruct the Green's function, and then you piece together the material response after that. Okay, so this is a new kind of quantum simulation that really targets response functions as opposed to static quantities of a system. Okay, let me now go on to the second topic I wanted to talk about, quantum computer-enabled optical receivers. There's also a paper we recently put out just on the archive. And this is more on so the previous one I talked about was more on the kind of algorithm side. This is more on the application side, I would think of. And this is work that was done in collaboration with students from Cornell and also UNM, University of New Mexico. And it was inspired by actually work that several people who are here at Arizona have done, including Saika Guha, Narayanan Rangaswamy, Kaushik Shishadharan, who I think is no longer here, but he was a postdoc here. And they have worked on similar things, and I'll call out some of that work in a second. So the question we have here is that is dealing with optical communication, classical optical communication, where you are transmitting weak coherent states over an optical channel, and you are doing it to transmit classical information, right? So you're using some phase shift keying technique. This is QPSK, so you send one of these 4 coherent states as a way to communicate 2 bits of information. By the time they go through the channel and get to the receiver, they're attenuated because of loss, and they're maybe also distorted because of the channel. And the task is to detect the output at the receiver and decide on which state was sent, or decide on the symbol that was sent. Now, it's been known for a while, including, so this is work by Giovanetti et al. And also Saika Guha, that you can't achieve channel capacities with this symbol by symbol detection technique, right? Where you take a pulse that's transmitted and you do a detection, you decide which one was sent, and then you do that over and over again. What instead you need to do is you need to do a joint detection of several pulses at once, and decode a code word that was sent. So what's the code word that was sent over these n pulses? And that's been known for a while, as I said, but it's not widely in use because it's very difficult to design and construct these joint optical receivers. It's a very non-trivial task, and SciCard actually has one of the only designs that I know of for such optical receivers for a particular modulation scheme. So what we thought about was what if you, instead of try to do that in the optical domain, you transduce first into qubits and then do a quantum computation as a way to implement the receiver. Right, so you take coherent pulses that are arriving, you transduce those into qubit states. In this case, these are just superconducting qubit states. And then instead of trying to build a receiver with knowledge of what the decoder might look like, you just train a variational circuit. So this is kind of like a machine learning approach to doing the decoding. Is you can construct variational circuits, quantum circuits, that you can train to decode which code word was sent, to reduce the error probability of that decoding. Right? And in contrast to designing the joint optical receiver, designing of these circuits and optimizing the circuits is a much more trivial task. Okay, so the key here is this transduction stage, right? So I said that you just transduce the optical field into qubits. Now that's not as easy as all of that. There are lots of techniques for transduction that exist. Most of these are usually formulated in the context of quantum networking, where you might want to network separate quantum computers. I'm really thinking about quantum transduction as a way to get unknown quantum states into a quantum computer in this case. And the transduction scheme that we spend a lot of time analyzing is optomechanical transduction, where you have an optical field coming in, you input it into a cavity, and one end of the cavity is actually a mechanical membrane, which as a result of the optomechanical force, optical pressure force, it vibrates the membrane, and it's also a charge membrane that changes the capacitance of a circuit, as a microwave frequency circuit. So this is how the optical pressure force couples into a microwave circuit here. You can write down the Hamiltonian for this system and show that you can indeed transduce the phase of the coherent state that's coming in into the phase of the microwave field in the microwave circuit, in the microwave cavity. You need a parametric pump to do this, but that's in order to match the energy differences, right? You have an optical field and you have a microwave field. You need to somehow bridge those energies, and that's done through a parametric driving source. Some of the non-idealities that you have to take into account with the system are things like cavity losses, thermal dissipation, because you have a mechanical system here, thermal dissipation of that oscillator. But you can do all of that, and what you figure out when you go through the calculation is that if you have a coherent state that's coming in the optical regime, that turns into basically this state, which is a displaced thermal state in the microwave cavity. So you incur some losses, so you go further towards the vacuum, and you also expand the uncertainty ball on that state. But importantly, the phase can stay unperturbed in that process. So this is a phase-preserving transduction mechanism. And so this is what we use. So we use this model for transduction to say that if you have a coherent state coming in the optical regime, you can turn it into this microwave mode state. And from there, you can use a conventional interaction between a microwave cavity field and a qubit, typically the Jaynes-Cummings interaction, in order to transfer the phase of that microwave field now into a phase of the qubit. So the optical phase can be mapped onto the qubit phase. So these are just a couple of examples. If you have BPSK signaling states, so you have plus alpha and minus alpha as the signaling states, that turns into these vectors on the Bloch sphere. Right? So I've two cases here. Let's just focus on the one on the right here. The blue is if you do the transduction at low temperatures, and the red is if you do the transduction at high temperatures. You can see that the red states are less pure. It's shrunk into the Bloch sphere, and this is a result of the heating that you incur during the transduction. But you can get almost distinguishable states in both cases, and that's ideally what you want is two states that are orthogonal to each other, right? Or close to orthogonal. They can't be exactly orthogonal because the initial coherent states aren't orthogonal, and you can't increase the distinguishability of them. But you can see that you can get fairly well if the amount of photons that you have is large. If the amount of photons that you receive is smaller, you don't get as a good distinguishability between those states. Okay, so now that we have mapped our information from the optical field into qubits, we can think about what computation you would do on this. And as I said, we're going to take the approach of just variationally optimizing over a circuit in order to discriminate these code words. And you can formulate a cost function that I don't think is so important to go into, but you can optimize those circuits, and this is the kind of result that you get, right? So this is a function of the received mean photon number, the amount of light you're receiving in the optical domain, and this is the probability of error. The black curve is the classical bound. This is the best you could do with the optimal symbol by symbol receiver, right? So if you're doing detection of each pulse, and the dots here are the error probability for increasing code word sizes. And so these are more and more qubits that you're decoding, and you can see that you can push the error probability down with increasing code word size, which is what you'd want to see. And this is kind of the quantum advantage here, right? Because you're doing much better than in terms of error probability than the best classical thing that you could do. And this is one of the things I like about this problem, is that this is not a heuristic advantage, because you can actually say what the best possible classical thing you can do is, right? It's formulated by a distinguishability bound, a Hellstrom bound. You can also think about the asymptotic case of asymptotically large code words and look at the capacity. And there's a lot of data here, but I'll just point out that the important thing is that this green line is the classical capacity. This is the best you could do if you had symbol by symbol detection. And these dash curves are what you get if you use this joint detection receiver. And in this case, that's right. Yeah. Right. You're just communicating one bit with each pulse. That's right. Yeah. Sorry. Yeah. I should say, if there's any questions, feel free to interrupt. Don't wait till the end. Yeah. Yeah.
The black curve on the left shows the pulse by pulse detection, and the dots are the word size with the qubits. That's right. So can you not do the word detection classical obtaining 3 pulses at once and then figuring out what the 3 pulses?
Yes. So that's exactly what the dots correspond to.
With the qubits.
So you mean do it optically?
Was can you do the similar word conversion in classical language? And is there any advantage of doing?
I see. So after detecting each pulse and then try to decode the code word just classically, right? So that doesn't get you to the capacity in this case, right? So as soon as you've converted that information from quantum to classical, the best you can do is this is that black curve. Yeah. Okay. So yeah, this is all in the case that I've only assumed noise in the transduction. I've assumed that the computation is ideal, but you can also show that this advantage persists in the presence of some amount of device noise in the quantum computation, which is something that I particularly like, because this could be a candidate for near-term devices where you don't have a large number of qubits and you still also have some noise, right? The quantum advantage here isn't resting on having a scaling in terms of your computer, having a large computer, right? It's resting on the fact that you're doing a fundamentally different measurement, a measurement that you can't do classically. Yeah.
It's your channel capacity.
So that's an asymptotic. The capacity is always an asymptotic thing, but so that's what even with 4 qubits, right, you can get this gap in terms of the error probability in this regime, right? So depending on what regime you are in terms of the received photon number. So if you have too many photons, if you have large number of photons, you see that there is no quantum advantage because you're essentially the signal is strong enough there that you might as well just do classical detections because those coherent states are almost distinguishable at that stage. I mean, their overlap is small. Yeah.
Now that you have quantum detection, why can't you just use say single photon states, either 1 or 0 photons? Wouldn't that
Right.
Get you closer to the capacity for a given
So-
number of bits?
If you're using that's a different capacity. But the reason we wanted to work with this is that here you're putting all of the task on the receiver, right? So the sender has simple classical, well, not classical, but coherent communication devices. So it's only the receiver that you're making more complicated. And the carrier, the channel is also kind of standard optical fibers and so on. So the idea here was to introduce the quantum feature as minimally as possible, not to kind of re-rig the whole system so that you have single photon transmission. Okay. So some extensions of this work. So I think of that particular result as a example of a more general framework that you could use, where you say, I'm going to take information encoded in some multimode light field, electromagnetic field, and I'm going to transduce components of it into qubits. And now I have the freedom of doing a quantum computation on those qubits, right? And before measuring and then doing classical data processing, right? So this is a notion of quantum computational imaging and sensing, where this is you can think about in this classical case too, where you do a detection and then you do a computation after it in order to make an inference. Whereas here the distinction is that even you do the quantum computation even before the detection, right? So you coherently process information in electromagnetic field. And so we're currently thinking about other applications, particularly in the sensing and imaging arena, about so applying this concept in that case. I think again the intuition here is really thinking about transduction as a way to get unknown quantum states into a quantum computer. Okay, so that's it for the kind of brief ads of some work, but I'm going to now switch into the deep dive into one particular result that we have. But I'll pause for a second there and ask if there's any questions about what I've talked about already. Okay. So this work is more on the resource estimation and performance assessment side of things, and it's also on archive. I've got the archive number there. And here we're really concerned with this notion of how do we establish trust in quantum computers? Right? These are going to be devices that are very complicated. How do we have any confidence in what they're spitting out? And so to motivate that a little more, let me talk about kind of quantum computing 101. Right? The central part of any quantum algorithm is the execution of a quantum circuit. A lot of quantum algorithms have a lot of other things around them, but there's always going to be an execution of a quantum circuit. And due to noise in the gates and environment and decoherence and so on, the action of the circuit is not going to be the idealized unitary that you wanted to implement. It leads to errors in the output, and even so there's typically two regimes you want to think about, like in that first plot that I showed. There's the near-term regime where you have NISQ devices or near-term devices where the output errors are going to be significant because you don't have error correction. But even in the long term, when you have error correction and fault tolerance, there are these devices are still going to have errors. Right? They're not going to be completely error-free. And so this idea of do you have errors in the output is still going to be relevant even in that regime. Right? This is not only a near-term concern. And most importantly, and this is really the crux, is that classical simulation of the circuit output is going to be nearly impossible in most cases, unless you have a problem where the classical output is already known, like for example, factoring, or it's easy to check at least. It's not known, it's easy to check. Right? So if you're trying to factor two numbers, you can always check easily whether the result is right. You can just multiply those two numbers out. But if you're doing things like quantum simulation, you don't have that check, right? You don't know if the output is correct or not. So that's the regime I want to think about. And this is not so far away, right? So in the next decade, we'll have thousands of qubits, hopefully, at least hundreds of qubits, and polynomially depth circuits. So these are going to be very complex devices. How do we verify the correctness of the output of these devices? Like I said, most interesting applications won't have output that's efficiently verifiable on classical computers, and microscopic modeling will be not be possible. So you can't just say, I'm going to have some confidence about each individual component on this quantum computer, and then therefore build up some confidence in the whole device. All right, so just to underscore the point that this is not so far away, here are two papers from 2021, 2023, where people have already used 100 qubit devices, roughly 100 qubit devices, to do very non-trivial many-body calculations. Right? And they've had to really work to see what the accuracy is. In some of these cases, they were just at the cusp where they were able to throw high-performance computing resources at it and say, yes, these answers are accurate to some error bars. But soon we're going to be even out of that regime, right? You cannot throw supercomputing resources at it. Okay. So this is an example of a really age-old problem, right? So as experimentalists would know very well, you build a very complicated device in a lab. How do you know whether it's working properly? Right? And so, like I said, one task is to try to just individually look at each component and build up some confidence in the components, and then build up some confidence that you're putting it together properly. But when you get to 1,000 qubits, 10,000 qubits, can you still use that approach? I would say it's not really feasible. And the solution I'm going to tell you about, we used two useful primitives to provide a answer to this question. I'm not saying that this is the answer. There's probably many other answers that you could true, but this is a answer to this question. And we use two primitives. One is time reverse dynamics, and the other is randomization. I'll tell you about how we use both of those. Okay. So here is the verification goal I'm going to set for myself. It's to estimate the fidelity of the actual circuit with the ideal circuit. Right. So I'm going to run some quantum circuit, and I want to have an estimate of the fidelity to which I've run that circuit. Okay. It's a quantitative metric. I want a number out that says, here is the fidelity. We're given a circuit of interest C, which is composed of arbitrary single qubit gates and 2 qubit gates that are self-inverse. What I mean by self-inverse is, right, doing it twice gets you back to the identity. So C0 is a good example of one of these. Okay. This is not an essential assumption. It makes some things easier. And crucially, we don't know the ideal output of the circuit. Okay, so this is how time reversal can be useful. This is actually a really old concept, echoing, or if you're familiar with Hahn echoes, this is exactly the same concept. You take your original circuit and you form what's called a mirror circuit, which is the original circuit followed by the time reversed version of it. Right? So you just invert the map, and you can do this on a gate by gate basis, right? You don't have to compute the output to do this, right? You just take this gate and you put the inverse of that there. Take this gate, inverse of that there. That's what the color coding means. And if everything was perfect, the output should equal the input, right? So you know what input you're putting in, and so the output should equal input. And so you can define something called a success probability, which is the probability that the output equals the input. Right? It's a measure of how much error there is in the circuit execution. It's not a fidelity, right? Remember, we want the fidelity of just the original circuit, right? This is telling you a success probability of the mirror circuit. But there's also other issues with this. One is that you can have cancellation of coherent errors, right? So you might have an error in one of these gates that gets perfectly canceled when you reverse that gate. So if you're doing forward evolution and you do backward evolution, you might just end up where you are just because you've canceled whatever error you had in your forward evolution. And obviously that's not good, because you're going to think that you're perfectly reproducing the input, whereas if you chop the circuit again in half, you ran the forward circuit, you would have errors. And then furthermore, the success probability isn't obviously related to something like a process fidelity. So that's the other issue with this approach. So we need additional ingredients. We need a more sophisticated version. And what we actually need to do is not run just this mirror circuit. We actually need to run samples from 3 different mirror circuit ensembles. Right? And I'll talk about what those ensembles are in a second. but we need to kind of expand the number of experiments we're doing. So what are these three ensembles? So let me sketch them out. So this is the original circuit. The first member of the ensemble, so this is a family of circuits, and I'll explain why it's a family, is that you do the same circuit in forward, with some small modification I'll talk about, but you do the forward circuit, the original circuit, then you do the backward circuit with randomized compilation. So randomized compilation is where you insert random single qubit gates around your existing single qubit gates, but you do it in a way that they actually don't do anything, because you can compute what happens when you do this random gate, and you compensate for that with the next random gate. Okay, so you insert randomization in a way that it doesn't actually, ideally, it doesn't affect the output of that circuit. And so you do the forward circuit, and you do a randomized compiled backward circuit, and you also do a couple of layers at the beginning and the end, which are just random single qubit layers. This is in order to randomize the input and the measurement basis. Right? So that's the first member of the ensemble. The second member of the ensemble is very similar, but you randomize compiled the forward version as well. So the first one, you did just the bare circuit in the forward case, but you randomize compiled the forward one and the backward one. And then the third member, or the third ensemble, is a really simple one where you just do random single qubit gates, and then they're inverses but randomized compiled. Right? So this is the minus one is the inverse of this, but you also do an additional random gate here. And the reason you have this is to measure the amount, or the estimate the amount of spam noise or state preparation and measurement noise. Yeah, Daniel. Yeah. Yeah. They don't compute, but you can easily compute what so these are single qubit gates. And so when I have a single qubit gates and I have two random other single qubit gates, I can commute them, because they're just 2 by 2 matrices, and then compute what the correction should be here, right, so that they don't do anything. Right. So they don't commute, but you can compute the corrections efficiently. Any other questions about that? Okay, so those are the three ensembles, right? So I call them ensembles because there's random elements in here, right? So each of these black or these white squares are random gates you're applying in order to do the randomization, and so this defines a family really, because each time you sample from this, that gives you a particular circuit. Okay, so why do we do this? Why do we define these families? So what you can do is you can look at the success probability of each of these families, and you can approximate them in this way. So the success probability of a circuit from this family is roughly the fidelity of your spam fidelity. This is how well you're doing state preparation and measurement, multiplied by the fidelity of your original circuit C, multiplied by the fidelity of the randomized compiled inverse circuit. That's this guy. Right, so the success probability is roughly equal to the fidelity of the components in this circuit. It's the spam correction, the original circuit, and the randomized compiled inverse circuit. And the reason this is, so remember, we can't immediately measure the fidelity of the forward circuit, right? But you can compute the success probability, which is the multiplication of these three fidelities. So if you have that, then you can do the same thing here, and you can look at what the success probability of this circuit is, and it's roughly the spam fidelity again, and then the randomized compiled version of the forward circuit, and the randomized compiled version of the backward circuit. And that's roughly, if you assume that the errors in the backward circuit are similar to the errors in the forward circuit, it's this product here. And then finally, the success probability here of this simple circuit is just the spam fidelity. Is approximately the spam fidelity. So if you stare enough at these three formula, right, and remember what you want to isolate is FC. Right? You have basically 3 equations and 1 quantity you want to isolate, and you can kind of put them together. If you want FC, you can take S1 divide through by S2 times S3 square root. And that will basically just isolate that quantity, FC. And that's what we call our mirror circuit fidelity estimate. Right? So if you can compute the success probabilities, which is basically, remember, how well am I reproducing the input to each of these circuits, that gives you a proxy for the fidelity. And that's the crux of the procedure. The actual formula we use is slightly more complicated, but morally it's exactly the same. It's the same concept that you can compute things that contain the quantity you care about, FC, and then you try to isolate that quantity by just dividing through and multiplying by the right things. Yeah. Yeah.
For the success probabilities.
Right. So this is a function of the error model. So if you have what's called a completely stochastic error model, which is you have no temporal correlations in your noise, you can show that these are equalities. But as soon as you have temporal correlations in the noise processes, they turn into approximate equalities. And I'll show you kind of empirically how approximate they are in a second. Yeah, so that's a function of the actual noise you have in the device. How well these approximations hold.
Yeah, how scalable is this procedure?
Stable in what sense?
In the sense of like variations in noise, like if you model the noise differently,
Right,
compared to what you have in hardware.
Yeah, I'll show you. I hope I can answer that question in the next slide. Yeah. Let me just see if there's other questions. Okay, yeah. So, the one slide after this, but so I said you have to do measurements of samples from each of these ensembles, right? So you might ask, how many measurements do I need to do? If you have a procedure here that is going to take so many measurements that you know, if it scales in any way with the number of qubits you have, this is not a scalable technique, right? But you can show that it doesn't. So basically, the number of circuits required that you need to run, it's the number of circuits of this from this family that you need, from this family that you need, and from this family that you need. That's N1, N2, and N3. And each Ni you can upper bound with something that's just a function of the precision that you want. Right? You notice that there's nothing here. So it's upper bounded by log of 1 on delta divided by epsilon squared, where delta is roughly the error probability, and epsilon is the relative precision of the estimate that you want. Notice that there's nothing here that is a function of the number of qubits in your device or the depth of your circuit. Right? If you had factors like that in there, this would not be a scalable technique. But it's just a function of the precision that you want in your estimate. Okay, so now here's some numerics to show you how well it works. So in each column here, each of these plots is a different error model for the device. These are numerical simulations. And I'm doing simulations on circuits up to 8 qubits, right? So each of these dots, depending on how darkly they're shaded, is anywhere between 3 qubit circuits to 8 qubit circuits. It's not so important what the actual circuit is. Let's see. So let's look at the first column. These are what's called stochastic Pauli errors. So these are errors with no temporal correlations in the circuit, right? So each error is completely random and stochastic and just operates on each gate after you do each gate. And these plots are showing the true process fidelity of a circuit. These are small circuits, so we can just brute force calculate what the true process fidelity is with the ideal. And this is the predicted fidelity using our mirror circuit fidelity estimate, right? And so this is kind of a correlation plot, and so you see that we lie on the straight line here. So we have almost perfect predictions of the true process fidelity in this case, in all these cases. So perfect correlation on the stochastic error model. This is an error model with stochastic Pauli errors and what are called Hamiltonian errors. We can think of these as correlated errors in time. And you see that we still have pretty good agreement between the predictions and the true process fidelity. There's maybe 1 or 2 outliers here, but it's still not so bad. And this is the case where you have purely coherent errors, purely Hamiltonian errors. And now you start getting more outliers, even though, on the bulk, it's not so bad, right? It was still on the diagonal here with our predictions. Now, the thing to stress is that for at least the existing architectures for quantum computing that we have, we think that we'll be mostly in this case, where you have a combination of coherent errors and stochastic errors, right? So we think that this will be a pretty good estimate in reality. Okay. I talked a little bit about scalability of the technique, right? So this is showing you predictions for 100 qubit circuits. Again, in numerical simulations, these are just Clifford circuits, so we can simulate them efficiently, and the errors are just stochastic Pauli errors, so we can simulate these efficiently. And so even for these large circuits, you see that the correlation between the predictions and the true circuit fidelities is pretty high. Okay. And so in ongoing work, now we're turning to experimentally verifying this technique. So we run it on these IBM cloud devices for small kind of circuits, and shown that it produces better estimates than two competing techniques. So actually, Daniel, how much time do I have? 15. Okay, that's good. All right. So 15, right? So these two, you might ask, what are the competing techniques that you might have to do this task, right? One, which is this black curve here, is similar to the task that I said. You can try to characterize each individual component and try to put it together. This is where we've taken estimates of individual gate error rates on this device and tried to piece together what the error would be for the whole circuit. Right? And you can see that it kind of overestimates the fidelity. Right? The fidelity is better than what the MCFE prediction is, which is the red curve. The other technique you might want to use is something called direct fidelity estimation. Now, this is another technique that you run a bunch of experiments and you try to back out what the fidelity is. But in contrast to MCFE, it requires many more circuits you need to run. And crucially, it also requires classical simulation of the circuit results. So it's intrinsically unscalable, right? You need to classically simulate the circuit to do it. But it's the closest thing to a competitor there is. And you see that it also, in a sense, it underestimates the fidelity of the circuits. Yeah.
Results, something about the true noise model, which is present. That is to say, stochastic versus Hamiltonian errors.
That's difficult because in these cases, right, we don't really know. All we get are these fidelity numbers. I don't know of any way to kind of back out more fine-grained information about the noise model that we have, or the noise you might have. Yeah. Typically, that's always the trade-off in quantum characterization, is that you have techniques that give you very rough estimates of the quality of the circuit that you're running. One is randomized benchmarking is a famous technique for this. This is another example where you get a fidelity estimate, but you don't get fine-grained information about noise processes. Usually to get fine-grained information, you need to have much more intensive techniques, like tomography techniques, to do that.
So is this also, I mean, behind the hood, like, is there some assumption about like your circuits being unitary to designs, things like that, like, or is there
No.
like that?
No, so the only thing we need is that we need the you need a random sampling of single qubit gates at the beginning and the end in order to do the spam estimate. So you need high random single qubit unitary. Yeah, but the circuit itself is completely general. Okay, so some of the ongoing work that we're doing is trying to do a larger scale experimental demonstrations of this technique. Another aspect is I'm very interested in trying to use these same two principles that we used here, time reversal and randomization, in order to develop protocols to verify analog quantum simulators. So everything that I talked about so far is for circuit model quantum computing. But there's this whole other model of quantum technologies, analog simulators, which maybe the biggest, the most successful example are these cold atom lattice simulators, where people do amazing many-body experiments where they take hundreds of atoms and try to predict things like phase diagrams of many-body systems. And they have exactly the same problem, right? So you're trying to compute something that's classically intractable. How do you know whether the result is accurate or not? And it would be great to have a verification technique for those analog devices too. And so trying to take the insights we have from the digitized model, the quantum computing model, and applying it to that case. It's something we're interested in. Okay. So that's kind of the summary. That's the topics that I wanted to cover. Just one slide on kind of looking ahead. I think we're in a very exciting era of quantum technologies, especially of quantum computing, where we're really tackling scaling of these devices. We have challenges on that path, a lot of experimental challenges, but being a theorist, I also like to think about theory challenges, and there's lots of those as well. I've listed some of these here. So scalable verification of quantum computer output, that's the topic that I talked a little bit about. Like I said, we should probably have more solutions to that. I don't think the solution that we had, the MCFE technique, is the end of that. Scalable characterization of large devices. This is getting back to your question about how do you know what errors you have so that you can improve your device? We don't have great techniques for scalably characterizing large devices. The tomography techniques that we have get very intensive very quickly. So how do we do that for large devices? Estimating or reducing the resources. So things like number of qubits, depths of circuits required for useful quantum algorithms. Some of the resource estimates that we have are very intimidating. Billions of qubits, depths, gate depths that are much longer than you could conceivably do these days. And so we need new techniques to kind of make quantum algorithms more resource efficient. And then finding new applications of quantum technologies, especially near-term ones, right? So depending on who you ask, this chasm between where we are now and where we'll have fault-tolerant devices is anywhere from years to decades, right? So if we have to wait that long to get fully fault-tolerant devices, it would be great to have some use for the near-term devices that we have in the meantime as well. So looking for new applications for those technologies. Developing classical software solutions to enable real-time interfacing with quantum computing. So decoding is a good example of this, where in the fault-tolerant regime, you're going to need a pretty powerful classical computer bolted on in order to do decoding of errors at the rates that you want to do real fault-tolerant quantum computing. And so developing the classical software and maybe classical hardware to do that as well. And then finally, maybe the deepest question in the field is understanding quantum advantage and where to look for it. Right? So we still don't really have an understanding of what provides a quantum advantage in a quantum computation. And so if we had a better picture of that, we could know, where to look for those problems that would give you a quantum advantage. And then, yeah, QuAAC, we're keen to tackle all of these challenges. We have interest in all this. And so if you have, if any of this sounds interesting to you and you're interested in working together, please get in touch. We have intern programs for students. We're always looking for postdocs. So we have internship programs for graduate students and undergraduate students. And so if you're interested, please get in touch. And I think, actually, let me finish with the acknowledgement slides. So of course, I'd like to thank all the members of QuAAC. Here are the people who worked on the particular topics that I talked about in detail today. And then most of our funding, especially for this work, is from the US Department of Energy, Office of Science. Thank you very much.
Well, feel free to ask a question to Mohan.
You talked about this three-circuit model where you find the fidelity by going making three measurements and then estimating FC.
Yep.
And then you said that you do this with IBM computer.
Yep.
And experimentally verify. Now, every time that you repeat the experiment, you get different numbers, presumably. Is it is it a repeatable thing? So every time that you do the same measurement on your system, would you end up with the same set of numbers that you estimate the FC, or do you have variations? And if you have variations, what was the meaning of the data that you showed? Was it average?
Yeah, so to compute that FC, you need to do many experiments to begin with. So you need to sample some number of each of those ensembles, and you need to repeat each circuit some number of times in order to get a success probability. So the success probability is a frequency of an outcome. So there's already a lot of repetition in there. But I think your question is, let's say we do all of that and we get a number, and then we wait a day and then we do all of that again, we get a number. You would get a different number. There's no doubt about that. So the most of the cloud devices are prone to things like drift over time, and yeah, even though they recalibrate devices once in a while, we typically see that the errors change, sometimes dramatically over the course of a day. So you would get a different fidelity. Yeah.
Is there a standard deviation that you should put on each one of those numbers? That
Yeah. So there are actually error bars on. There are bootstrapped error bars. You can kind of see them here, but in all the other ones, they're so small you can't see them. But remember, this is not doing that experiment that I said where you calculate a fidelity, you wait some time, and then you calculate that fidelity again. Right? That we haven't done, but given what I know about those devices, I'm sure that those numbers will be different. Yeah.
Very nice talk. I have a couple of questions. So first one was, have you looked at like the variation and the fidelity with the depth of the circuit? Like, does it change a lot?
Yeah. So the fidelity does. So these circuits, the larger the number of qubits, actually, these are QAOA circuits. I don't know if you're familiar with them. So the more qubits you have, also the higher depth you have. So yeah, so you can see that the ones down here, the low fidelity ones, are mostly the light blue ones. So they are also the longer circuits. Yeah.
Algorithm or answers. Like, I'm trying to see how particular these numbers are. Like, what exactly it's characterizing? Is it characterizing? I guess it's characterizing only the QAOA answers.
So these plots are, but the technique itself is not dependent on any particular circuit structure. So you could do it on any circuit. Yeah.
Same depth, if I picked a different algorithm.
Oh, I see.
It's a different circuit with like similar depth, similar number of qubits.
Right.
Would I get a similar number, or how particular this is to the kind of gates that QAOA has compared to other algorithms?
Right. I see. Yeah, we haven't tried that. But I would assume it's dependent on the structure. Like, so, roughly it's the number of 2 qubit gates that matter. But we could, that's not the only thing, because if you look at the predictions, like these predictions are basically based on that intuition that you just count the number of 2 qubit gates, you know how much error each 2 qubit gate has, and you just multiply it up. And so that's not the only thing, but you would think that circuit structure matters somewhat.
And the second question was, so ultimately for near term or longer term, if you have some kind of error correction in the system, then what you ultimately care about is what is the fidelity at the logical level, like
right,
that the qubit see. Like, have you thought of elevating this? I know there's like logical randomized benchmarking that Steve Lamia and others did.
Right.
Have you thought of a similar thing for your?
Yeah. So you could do. We haven't kind of done any rigorous numerics or anything on this, but you could take the exact same approach, right? So time reversal looks exactly the same. You would just do logical time reversal. And the randomization looks exactly the same as well. The only trick is that if you're trying to do logical randomization at the 1 qubit level, you need to do a many qubit random unity, right? So that's the only part that's difficult. I think you can get away with just doing single qubit unitaries on that as well, because you don't. I don't have.
Yeah, the reason I'm asking is because like if you only care about, you say doing QAA at the logical level,
right?
Then there are many equivalent like many different circuits at the physical level that have the same logical effect. So there's
I see.
like this blown up degrees of freedom for implementing the same algorithm. And so it's not clear what the fidelity estimate, is it estimating like an average or all possible solutions of implementing the same algorithm, or is it implementing one instantiation of that?
It would be one, right?
One,
Because
right.
there's always a fixed target circuit that you're working with.
Yeah.
Yeah. And you could
Right.
actually, so just think about it, you could take the logical circuit, eventually it has an implementation at the physical level, and you could do the same thing at the physical level. And you would get an estimate of that fidelity. But it would be a physical level fidelity.
Yeah.
Let's ask one last question to Mohan, and then the other question you can approach Mohan afterwards. One last question. Okay, if not, I have a question. So I was gonna give you some blunt and straight question, where the advantage of quantum computer comes from, and your last slide says that we don't know yet. So, okay. Is it coming from mostly from tensor nature of the quantum system, like Hamiltonian goes exponentially large, or does it come from superposition, or does it come from entanglement, in your opinion?
I wish I had an answer. I had no idea. So people have identified many ingredients, like the scaling of the Hilbert space is one. The entanglement, the fact that you have entangled states is one. But I don't think any of them are satisfactory answer, especially any of them by themselves. And so, entanglement, for example, we know that if you have too much entanglement, that's not universal for quantum computing. And so they can't be any one of those things. I think it's a much more subtle ingredient, which I unfortunately don't have an answer to. I wish I had an answer.
Yeah, let's thank Mohan again.